this is a Hillbert approximation stuff. Linear approximation in Hilbert space. And the main thing is the orthogonality principle, where if you have this some arbitrary point x, and then we want to find a point, the x hat we will call it, that lies in this some subspace T that best approximates this x. And what we mean by best approximation is minimizing this difference, this distance, and we can represent it as x minus y, x minus y, where this is the y that lies in this T. And while this is like two-dimensional or example, where, well, this could be three-dimensional or four-dimensional and so on and so forth, and it doesn't need to be just like one point, it could be like the whole, like the function. So if you want to approximate some functions with like limited linear, some nonlinear functions with the linear pieces we have, we can use this principle. It makes sense that the x hat will, the best represent this x will be, so we can draw this line, and then we notice that this line and this lines are perpendicular or orthogonal. So this line is, we call it x minus x hat, that's this line, and we have t. So we can know that this x minus x hat and this like line t would be orthogonal, and that is really the orthogonal principle, which is this. Okay, we don't really need to know the proof, because the intuitive kind of makes sense, and we can. So I talked about how it can be used for like approximating the function, some function, and x hat will be some combination, linear combination of some function where we have this building block function of v1, v2 all the way up to vn, and then for each of them we'll have some corresponding coefficient a1, a2 all the way to an. They kind of manipulates the magnitude of each like pieces or building blocks, and we can use like the Graham matrix to like kind of simply calculate it. And how it happens is, so orthogonal principle, so we just learned the x minus x hat, that's this line, and then the vn, so that is the building orthobasis of the subspace T, so you can just really think of it as T. And it makes sense that it should be orthogonal or perpendicular, and because of that, this inner product should be 0, because inner product is really dot product, or you can think of it as the projection onto each other. And if they're truly orthogonal, like if I project this line onto here, it will be just like a point in space, and the length of the projection will be 0. Or so, for example, if it's not orthogonal, I say my line is like that, then if I project it here, well, actually this is too long, but okay. Let's say if it was like here, like up all the way to here, then if I project it onto T, my line would be like this, like so here, so it would be like this long. So it will have some length, whereas if it's orthogonal, well, no matter how long it is, if I project it onto the line T, it would be like 0, the length would be 0. The projection of the length would be 0. Anyway, going back, so this should be, this x minus x hat and T, they're orthogonal, so their inner product should be 0. So that's where we are at. Instead of T, we just use Vn, which is the orthobasis for T. And then, because we know x hat is the combination of this like linear, some like building block function Vk, we'll go from V1 to V2, V3 all the way to Vk, or Vn. And A is like the coefficient for each of them. And we can use like move stuff around, so this goes over here, so xvn over here, and then we still have the same thing, and the A is just like a constant, some number, so we can pull it out front. So that's how we get that. And then we can convert it into like GA equal B form, where this is kind of like flip-flopped here. So this is the B over here. So that makes sense. X is the thing we want, or a thing we are trying to approximate. So that's the true, like the function ground truth. The Vn is just the building blocks we have. And then A, just A is here. A is the corresponding coefficient for each, like the building block V1, V2, V3, Vn, like those stuff. And this is a Vk, Vn, and over here. So for, if you think of like so let's say like k is equal to like 1, so we would have like V1, so this is V1, and then we have, but we also have like n component, so it would be V1, so Vk equal V1, and then Vn equal V2, and then da 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 all the way to Vk equal V1 and Vn equal to some, I don't know, some number. So that's how we get this first column. And then we're going to go to, now the k is equal to, next one, k equal 2. So V2, so this column we do the same thing, V1, V2, we do all the way to like V2 equal Vn. And then we just go all the way up to k, Vk, where k is equal to n, so we get this column. So that's how we get this Vk, Vn inner product becomes like that. So this is G, this is A, and this is B. And what we really want to know is A, because we already know what we're trying to like approximate, the X, right? And we already know that the ortho basis, the Vn, or Vk, or so. What we really want to know is like how much of each ortho basis do we need to best approximate the function, the X. So what we really are interested in is A. So we're going to rearrange this equation Ga equal B into like A equal G negative 1B, and but notice that G is like a kind of symmetric. So there's like V1 and V1, Vn, Vn, V1, like, so these are like kind of like symmetric if you kind of get it. So even if you change it to from G to G negative 1, the only thing that really changes is the sign of each, these inner products. So to give an example, you can do this thing, and you kind of just flip this way, and then flip the sign this way, and then you get the determinant, which is this. So this times, and then subtract and then put it under 1. So for example, it would look like this. If you had G equal 3, 1, 1, 3, then I would flip this 2, so 3, 3, flip the sign this way, negative 1, negative 1, and this is determinant, which is 3 times 3, 9, and then negative 1 times negative 1, which is 1, so I subtract that from 9 minus 1 is 8, so 1 over 8, this. So this would be the G negative 1, and then if I were to do this, it would be so G negative 1 and then B, which is 2, 0, which is specified here, up here. And then we'll get some like A, so this is 2 by 2, and then this is 2 by 1, so we'll get some 2 by 1 matrix as a result. So and then get that. But this is you 2, 0, 2, 0, so 0, 0, this becomes a 0. So 2 times 6, 2 times 3 is 6, and then negative 1 times 0 is 0, so add them up is 6. This row, 2 times negative 1 is negative 2, and then plus 3 times 0 is still negative 2. So that's how we get that. Yeah, that's A. So in this case, so that's A. So we know that the final answer of x hat is like a times like a1 times v1 plus a2 times v2 plus, an to vn. So a1 is 3/4, right? And then a2 is negative 1/4. So that's how we got that, 3/4 and negative. And then this is v1 and v2, which was specified here as the span of this subspace. So 1, 1, 1 goes to here, v2, which is 1, negative 1, and negative 1 over here. And then you do that, add them all up, you get this 3D coordinates, and that's our x hat. And then x was this, and then you can see the difference. You can calculate the x minus x hat, and this minimizes the norm of this. And to ensure that our answer is correct, we know that x minus x hat should be perpendicular or orthogonal to the t. And so here I did it as x hat because I don't know why, but I did it, and it was still 0. So which is, I just take dot product, so half times negative 2.5, 1, 0 is just 0, and then this is positive 1/2, and then 2.5, so they cancel out to become 0.